Okay, I think we'll get started. So today we're going to talk about computer simulation lab. We'll go through the computer simulation lab for a random walk on a Poincaré disk. This is just part of a project that I've been working on that deals a lot with the Poincaré disk, but I feel like this is a standalone video, so you could be coming to it just directly for this alone. Now, for those of you who don't know, the Poincaré disk is one of 3 or 4 good ways to represent the non-Euclidean geometry of negative curvature or hyperbolic geometry. And how the disk is laid out is that all of this non-Euclidean space fits on the unit disk inside the unit circle. So this blue circle here is a circle of radius 1. And any point in this space is inside this disk. So what that means is that all of space, including infinity, is in here, and as we reach the edge of this disk, we're approaching infinity. And the infinity lies then, the point at infinity lies on the unit circle. So how things behave is when we're close to the origin, things are quite like a Euclidean geometry, but as we progress outward in any direction, space becomes much more compressed. And so the same distance step, if I step in one direction near the origin, is going to appear to us much bigger than if I'm taking that same size step out here towards the edge. Now, one of the key ideas in any geometry is what constitutes a line, or the shortest distance between 2 points. Now, in a Euclidean space, if we have any 2 points, then the shortest distance between 2 points is our traditional line, and that's indicated here in blue. And these 2 points lie on that line, and they constitute a line segment, and this line extends out to infinity in all directions. Well, in Euclidean hyperbolic geometry, the situation is a little bit different. The distance between 2 points is not a straight line like this. It's actually the arc of a circle. And so it's the circle that passes through both of these 2 points and intersects the unit circle at 90 degrees. So there's one and only one of those. This is called the geodesic, and this would be called a geodesic segment. Notice here now, if you aren't used to this geodesic here, including the dashed, is an infinitely long line. And this constitutes then a line segment of some finite length. And there are formulas for calculating this length. We won't go into that in great detail here. All right, well, so in order to achieve this behavior, we have to endow the unit disk with a metric or a measure of distance that accounts for the fact that distance is getting compressed as we get out to the edge of the circle. And that metric is called the Poincaré metric. And it's given by this well-known formula here. Don't worry too much about the 2. That's somewhat of a convention. You do see sometimes this with a 1. What's important here is this denominator. So the numerator is the same as the Euclidean, typical Euclidean distance. So this is basically the Pythagorean theorem. Here, we have that in the numerator, but the denominator is 1 over x squared minus y squared. And if we notice this here, that's x squared plus y squared, negative. So this is really 1 over r squared. And so we can see here why things get weird at the unit circle. Because at the unit circle, r is approaching 1. And so this is approaching 1 minus 1, or 0. So it's making the denominator very, very small. And so if the denominator is very small, the distance covered is a big distance. So as we take a a little bit of a step here, it gets divided by a very small number, and it constitutes a very large distance. So as we go from here to here, we're covering a very long distance as compared to the Euclidean metric, which if we have a point anywhere in the disk, the Euclidean metric just says that's our distance. So wherever we are, it's the same length. But the Poincaré gets shrunk, it gets elongated considerably because of this denominator. Okay, so how is this going to affect the random walk? Well, let's imagine the Euclidean case first. If I have some point here, we're going to just have the computer simulate this random walk. There's lots of different ways to do that. How it's going to be done here is that at any given point, it's going to choose some direction at random and then take a finite step in that direction. And that step will, in the case of a Euclidean geometry, be a Euclidean step. In the case of the hyperbolic geometry, be a hyperbolic step. So the distance is always kept the same, and that's what we'll call the step size in the simulation. So then the particle ends up over here, then maybe another random direction here, 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 and so on. And if we were to watch the path of the random walk and look at any given step from one step to the other, this distance will always appear to be the same, right? And it will be the same. Now, let's see what happens in the hyperbolic case. So in the hyperbolic case, we're confining the step to be the same distance, the same hyperbolic distance each time, not Euclidean distance. So if we're here and we get a random step, that's going to look very much like the Euclidean step. And in fact, if we're right at the origin, it'll be equivalent to the Euclidean step, because that would say r is 0, and we just have the Euclidean metric. Now, as this goes, and we start to get out further, then any given step is going to start to compress, right? Because if we were to keep this same step size here, we would be covering a lot more hyperbolic distance if we're out towards the edge. And we're always fixing the hyperbolic distance to be the same. So we're taking an equivalent hyperbolic step each time. So what we would anticipate seeing is a compression of the steps down here. Now, the other thing we will have to think about too, if this were a Euclidean, just stuck in the Euclidean circle, then we would be random walking all over the place. And as we got to the edge of the circle, well, we might be just as well see the particle come back to the middle. But as we think about this Poincaré space, what is happening here, this is infinitely big. So instead, the analog in the Euclidean case would not be confined to the circle, but to all space. And so if a particle's random walking over time, eventually it will end up quite some distance from the origin, and finally off, just kind of get lost to the vastness of the space. Well, that's what we would expect to happen here inside the Poincaré disk. So if we let this go long enough, then it will spend most of its time near the edge, because there's a lot more space in this little annulus than there is in this whole centerpiece. And so we should expect, if we start it in the middle, we'll kind of oscillate about the middle, or randomly walk around the middle, and then when it gets out to the outside, it will then stick out there, stay out there. Okay, so that's going to be our first experiment. And this is just a random walk of a single particle, and we'll trace the path of that particle as it goes. The next experiment, we're going to put a whole bunch of particles in the middle and let them all random walk. We won't follow their paths, but we'll just let them randomly walk through the disk, get a feel for that. What we're going to notice there is if we let it run long enough, this same phenomena. We're going to lose particles to the outside of the disk. So we're going to keep track of the radial distribution of these particles, how many particles at a given radius normalize to that radius. So make little annuluses and count how many particles are in each of these, divide by the radius, and we'll get a radial distribution as we go out. And we will see what appears to be, but really isn't, a repulsion of these particles out to the outside. And all we're really seeing is that we're zoomed in on a particular piece of space here, and it gets distorted out here. So there's just a lot more space out here. So as time goes on, those particles, we're just going to lose those particles to the vastness of that space. So what we're going to do then in part 3 is we're going to look at that compared to the Euclidean disk. So we'll watch diffusion on just the Euclidean disk, and then we're going to add a little repulsion to the Euclidean disk and see if we can get something similar to what we're seeing in the hyperbolic disk, but we'll see that we can't get it exactly the same because the geometry is different. And then finally, part 4, this is an optional piece. If you have never heard of Lie algebra, then you could stop watching at that point or just kind of follow along and come out the other side. If you haven't heard of Lie algebra, but you've heard of vector fields, basically we're going to put a vector field on the Euclidean, or on the Poincaré disk, and watch how that impacts the diffusion. So there'll be a time dependence to that flow of those particles, or there'll be a deterministic flow as well as the random walk based on the vector fields. And we've just chosen the vector fields to be the generators for the Lie algebra, and those include a rotation and boosts along the geodesic, so pushing a particle along a geodesic. Then you can make combinations of those called the ladder operators, so there are a couple extra vector fields we'll look at. So if you've had some familiarity with Lie algebras, it's kind of a cool visualization of the Lie algebra of the Poincaré disk, which is homomorphic to the SU11 group. So the SU11 group, really the PSU11 group, is the group of automorphisms, is equivalent to the group of automorphisms of the disk. And so the SU11 algebra is appropriate for the Poincaré disk, and you can derive it right from the Mobius transformations that constitute the makeup of that. So if that was all gibberish, don't worry, just follow us through part 4. If that was something that you're familiar with, then that's another dimension to this this lab. All right, let's go to the computer and go through running the lab. Okay, so let's first show you where to get everything. So if you go to darrenolness.com, and we'll go to Utilities and Poincaré Disk. This is where you can find the single program that will launch all of these different pieces. It's called the Poincaré Diffusion Launcher. You can also find the laboratory manual. I'm not going to print this off and look at this. I'll just take you through it, but if you want to kind of go through it, talks a little bit about the distance formula, goes through the algorithm for the random walk, and I'm still not completely happy with the algorithm. And those of you who are familiar with hyperbolic geometry, you might notice that there could be some improvements there as we look at this. And then finally gets into the lab procedure. So we'll just walk through this lab procedure, roughly speaking. So I'll just kind of follow what you would do there if you're doing this on your own. Probably you shouldn't just grab a program from some random guy on the internet. So if you want to just follow this and then try to write your own program or something like that, you can do that. I do have the let's see, let me go back here. Do have the programs on GitHub. I use ChatGPT a lot to get all the organization of the GUIs and that sort of thing. So it's definitely a ChatGPT style code, but it writes good code, so better than I can do. So it could be something you could look at too if you don't want to just run the program directly. All right, so that's where you would get everything. I've already got this on my machine. So let me go ahead and run the Poincaré Diffusion Launcher. So what you will see here if you do run it is just a listing of the different pieces of the lab, a link to the GitHub repository, and a link to the web page for the lab that we just came from. All right, so let's start with part 1, and let's do this random walk. And hopefully it'll start here. Okay. Couple of things. I should have just had the default here as one update every step. My computer's fast enough to do that. So if you have a slower computer, you could leave that as 10 and it'll take more steps before it updates the screen, kind of help with the computational demand. You'll notice we're just going to leave the speed here as is, but we have different step sizes. We'll start with a small step size and run this, and then we'll see what happens when we get to a larger step size. So we'll run a couple of times. So go ahead and start this, and we see this random walk, and it's going to look an awful lot like a random walk near the center of the disk, because near the center of the Poincaré disk, it's quite Euclidean. But as we get to the edge, the steps will compact. Now, what we'll see here is the step size is so small that it's going to take a long time, probably. I mean, it's all random, but take a long time to get an excursion out to the edge of the disk. So basically here what we're seeing is a normal Euclidean walk, more or less, because we're very close to the center. Now, let's stop this and reset, and then let's take the step size, make it a little bigger. And now it'll take a much larger hyperbolic step. And so what that will do then is it'll take a much larger hyperbolic step, so it'll get out to the edge a lot faster. And so here we're seeing Euclidean, and now you see this compactification. And here's where I'm not quite happy with my random walk. It's taking too big of a rotation, but you see this very much compacting around the edge, and it's just doing a random walk, but it's much further away from the origin, which is compressed in this edge. So each time it's not taking any shorter steps, but each time it's taking in terms of its radial distance, but each time it's just appearing to be smaller because of the nature of the disk. All right, I'm going to pause. I'm going to reset this, run it one more time at this step size. And we see sort of a normal Euclidean behavior. And then as soon as it escapes the origin, it has so much space to roam, it probably won't come back. Now, it certainly could come back to the origin. I've run a few of these and never really had it come back. Sometimes it came back somewhat noticeable, but that's really going to get it stuck out there at the edge, and we can see here it's basically on the unit circle, which is getting way out towards infinity. All right, so I'm going to close this program, and let's just do diffusion now. So what we're going to see here, I'm going to increase the number of particles to 15,000 and take my steps back to 1. We're going to see 15,000 particles placed at the origin, and then we're going to let that diffuse. This is calculating the radial distribution, so it's calculating how many particles are in a given annulus of a certain radius, and then dividing by that radius. And so what we will see is that initially everything will be compacted towards a 0, and then that will spread out. But as we expect, this should start to go all the way to the edge. And so our radial distribution function will slide across. Now, we'll do a small step size, and let's go ahead and run this. And you can see here our radial distribution function very close, but it's gaining values out here. And now again, with a small step size, it's going to take a while. If we were to let this run, we would expect all the particles basically to get all the way to the edge. So we'll just run this a little bit longer, and then we'll pause it and restart with a larger step size that will get those particles exploring the space a little faster. So let me pause this, reset here. Now I'm going to increase the step size a little bit. See if this is enough. So we spread much faster. We're getting now we're starting to see a buildup on the edge, both visually and then also with the radial distribution function, as we're losing particles from the origin and heading out to the larger reaches of the space. And if we would let this go long enough, we would see very, very few particles in the middle, and then finally probably none, even with 15,000 particles. Since the space is infinite, the average density is going to be very small. Maybe you can see it really clearing out here. Now I'm going to run this one more time, but imagine this now not thinking about hyperbolic space, but thinking about just a regular space, and imagine what the particles are doing, what it looks like they're doing. So I'm going to pause this here and reset and restart. And so it looks like there's a repulsion in the middle because particles are starting to clear out of the center. I'm going to pause this, reset, and I'm going to increase the step size now. And you can kind of see that almost look like a wave. Let me pause, reset this. I'm going to go a little bit more. Kind of a sort of a wave of the particles gets pushed out. So this, I refer to this, I don't know if this is a real thing, but I refer to this as this apparent hyperbolic repulsion. So let's dig into that idea a little bit. So let's open up this hyperbolic repulsion program. And now what we're seeing is, and remember to change that to 1, we're seeing the Euclidean disk over here and the hyperbolic disk over here, the Poincaré disk over here. I'll put 15,000 particles. And just watch, let's run it, we'll run it a couple times. Let's just watch, let's focus on the Euclidean disk here. And let's see what happens. This drift strength, I'm going to put that to 0. So this is just going to be regular random walk on a Euclidean disk. I'll make this a little bigger. And so what do we expect to happen? Well, we expect this now to form a uniform density on the whole disk. And because it's finite, this density won't go to 0, so it won't clear all the way out. Let's go ahead and start that. And we see the radial distribution here. So the radial distribution should become uniform. And as time goes on, we begin to see that happen. And then we'll reach sort of this steady state, although there's still obviously particle movement, but this sort of steady state in terms of the density of the particles. And it will become uniform across the disk. And so we're seeing that happen there now. Okay, well, let's see if we can make this Euclidean disk behave more like the hyperbolic disk, where we can slide the radial distribution over. So we put a radial drift in here. So that means it's trying to drift out along the radii. It has a drifting force along the radii. So I'm going to tune that up a little bit, and let's go ahead and start and see if that's enough. And we can even see a little dip here now, and we get a push over, starting to see a increase in density around the edges. Now, this will never look exactly like the Poincaré disk, because eventually the radial distribution will essentially go all the way over to the farthest bar over here. And that can't happen here because our step size is bigger than that bar. So I suppose if we had even a really, really small step size, we could get everything stuck over here if we had a really strong drift force. I'm going to just increase the drift force a little bit, make it a little bit more noticeable. Faster climb, and we fill that. And let me go back to 0 again. And now everything fills in. It distributes inward. And let me pause this, reset, increase the step size so that we see this happen over here on the Poincaré disk. Now the Euclidean disk will come to equilibrium much faster, and the Poincaré disk will slide its radial distribution out much faster. So the Euclidean disk came to equilibrium almost in no time, and then we see this same behavior we saw before in the earlier part of the experiment. Okay, let's look now at the final part of the experiment. This is dealing with the Lie algebra for the SU11 group, and we're going to look at the effect of the generators for that algebra. And so let me first show you what those vector fields look like. So we have one generator that geometrically is a rotation. And so the vector field, this is a vector field drawn as streamlines, has this net rotation to the field, and that's the K1. So let's go ahead and run that. So I'm going to put the field strength up here, get the number of particles up, and number of steps per update down to 1, and then let's choose the K0 or the rotation generator. So what we want to look for here is this diffusion coupled with a net rotation. It looks like I plotted my vector field the wrong way. That's just a convention. So should have had the vector field lines going the other direction. So we see this rotation of this. Particles are driven along circles here, but also coupled with diffusion. Can increase the step size, give that a try. Still get the same behavior with the larger step size. We accumulate out at the edge of the disk, but now we have this net rotation of all the particles. I think I need to break this a little smaller here. Let's look at these boosts. So there's going to be a boost. So that what the boost is, well, let's look at the vector field. So these are pushing the particles along geodesics. So especially as we get up here, you notice these are circles, and they intersect the unit disk at 90 degrees. Sometimes that's hard to see, but they're intersecting at 90 degrees. Something that's right along here is basically a circle of infinite radius. This is a circle of a very huge radius. And so this is the boost profile in the x direction. Very similarly, this will be the boost profile in the y direction. So we'll just run one of these, so we'll just run the x here. So let's go ahead and we've got it boosted in the x direction. Let's go ahead and run it and see what it does. So we get this distribution that sprays outward and shifted to the right. So notice no particles have escaped to the left. That one was trying to, but doesn't quite get there. And so finally, the last particle escapes out to infinity, gets pushed out to infinity. Finally, the ladder operators are complex combinations, linear combinations of the boosts. So it's boost x plus I times boost y. And honestly, I don't have a good feel for these vector fields. We usually use the ladder operators in terms of their algebraic structure of moving from one, say, quantum state to another quantum state. But here, as combination of vector fields is interesting. The plus operator looks like this. That was unintuitive to me. Hard to know even what these are. They're circles. They're not horocycles, which would just always touch the edge, and their centers appear to move this way, but I'm not quite sure what this structure is. And then it turns out the minus cleans right up because it subtracts the y component, and we end up with a drift, but it's not a geodesic drift. These are straight line drifts. So when we do this one, we'll try to keep in mind the geodesic drift, which sort of sprayed outward. This is just going to push everything to the side. So why don't we do that one first, kind of get a feel for that, and then we'll come back and look at this is kind of the coolest vector field, this plus one. So I will choose, stop, reset, choose. We'll start with the ladder minus. So we expect now just a drift that looks a little different than the boost. So let's go ahead and run this. It was a little bit hard to tell, but pause, reset, let me run the boost. So this is the boost now. Little more of a spray there because those outer ones get pushed up like that or pushed down like that. And finally, let's look at this one. This is kind of a neat one. I'm going to increase the field strength so we see the effects a little more. So a lot gets shot out to infinity, but many get looped around. So let's go back to this picture. See, they're getting looped around and recycled here, also getting shot out to infinity, which we saw. So we're spilling a lot of particles out to infinity. So eventually this will probably clear out, but we're getting pushed back in here. We're sort of concentrating this side, pulling out of this side. So that's kind of an interesting behavior there. Now, there's nothing I mean, certainly these vector fields are special, but you could imagine any kind of a vector field on this disk, and the particles would respond both with their random walk and with the effect of that vector field. All right, so I think that was everything that I wanted to show you in this lab. Hopefully you kind of got a feel for this interesting look at the hyperbolic geometry here with this random walk. I encourage you to play around with it, make your own program if you're interested in that. Fiddle around with the type of random walk. Maybe you want to do like a taxi cab walk or something like that. I didn't put, other than the radial distribution, I didn't do any kind of statistical analysis. So it'd be fun to, you could include some kind of statistical analysis. You could time how long it takes to have a inversion of that radial distribution function. So I think there's lots of things that you could take and go and run with this lab. All right, that's it.